Section 3.7. Yes, you will notice we skipped section 3.6. And that is because section 3.6 is about light and energy, electron levels, and there's a whole lot more to that than our book can do justice and what we need to spend time on. Heck, Einstein won his Nobel Prize with his study of light and photons. So it obviously is really deep, and it is very important and very exciting. However, we're going to take from that something called the electrons in the outermost energy level. So just go with me on this one. All right. So as we look at the periodic table, blanking out the transition metals, the reason why there's the chemical properties in our different elements is it's actually due to the number of valence electrons. Not that you know what a valence electron is, not yet. But now then, let's look back at the last slide to make sure that we realize what we're talking about. Okay, last slide. So, our first slide here, everything here is in the first family and our second family, and you will notice our transitionals would normally go right in here, but we've blanked them out. All right, moving forward. So valence electrons are the number of electrons in the outermost energy level, and the outermost energy level is back in chapter 3.6. So don't think you're going to miss out here. I'm just going to cut through the chase and get you what you need. Here it is. The group number gives the number of valence electrons for the representative elements. Okay, so that's nice and easy. In the first family, the first group, there's one valence electron. In the second group, 2A, there's 2 valence electrons. In group 3A, there's 3. I think by now you can get the point that by the time we're going all the way across the periodic table, of course, blanking out, ignoring the transitional elements, we get to group number 8A, and there's 8 valence electrons. So see, that's what we needed to get from our last section, 3.6 that we missed. All right, so can you find how many valence electrons are in each of the following? And at this point you may go, who cares? Well, actually, it's really important because that's where all the action happens. That's where all the reactions take place is with those valence electrons. So actually, it's very important. And when we get near the end of this section, you may go, is that all there is to do with valence electrons? And that answer is heck no. We'll continue on in the next chapter. So, let's go ahead. Calcium. When we look at calcium, calcium is in the 2A group in the second family, so that means it has 2 valence electrons. All right, press pause and see if you can do the rest of these. Okay, so when you look at the periodic table, lithium's in the first family, so 1 valence electron. Nitrogen is over there in group 5A, so 5, etc., etc. All right, now then, we're going to use these valence electrons and use them as symbols with dots. We're going to need this again for the next chapter when we're talking about bonding. And so aluminum has 3 valence electrons. And so notice that we have 3 dots placed around 3 of the 4 sides of our element. So aluminum has its 3 valence electrons. Here's 1, here's 1, and here's 1. Okay, so as we write our Lewis symbols, you'll notice that for magnesium has 2 valence electrons, 2 electrons in the outermost energy level. So you can see that right here if you want back from the last section, but don't worry about that. Just know it's 2. Why? Because it's in the second family. It's in group 2A, so you know there's 2 valence electrons. So you can write the 2 valence electrons in more than one way. Notice it's not picky about where you're going to be putting those valence electrons. All right. So, here are some examples in table 3.11. So let's look at hydrogen or lithium or sodium or potassium. They all have one valence electron. They are in group 1A. You will notice there is one dot beside all of them. Group 2A, 2 valence electrons. There are 2 dots to write the electron dot or Lewis symbol for beryllium or magnesium or calcium. Again, you get the point. And we come all the way over here to 8A. Now here is, notice though, helium only has 2 electrons. Why? Because helium, look at the periodic table, only has 2 protons. So helium's the exception to group 8A. It doesn't have 8 electrons to have 8 electrons in its electron dot symbol. But all the rest do. Like neon, notice neon number 10, 10 protons, 10 electrons total, but there's only 8 in the outermost energy level. And you go, wait, what did you just say? Well, that was back in the last section. We discussed that. Actually, we didn't discuss that, but that's discussed in section 3.6. That, just take my word, in group 8A, except for helium, there are 8 valence electrons. So here we go. Write the electron dot symbol for each of the following elements. Chlorine. Well, we look to see what group it is. Oh, it's in 7A. So that means we're going to need to put 7 electrons around it. Now, we pair them up once we have gone around the 4 sides individually, then we start pairing them up. So, as you look at this, actually what you first do is you first draw 1, 2, 3, 4, and then there's still 7, so we're going to pair them up 5, 6, and 7. All right. So carbon only has 4 valence electrons, so again shown representatively 1 on each side. Nitrogen, again, we start out, it has 5 valence electrons, it's in group 5, so we first start out with 1, 2, 3, 4. Now then, since it's got 5 valence electrons, we need to pair it up with one of them. It doesn't matter where you're going to put the paired side. Okay, so another trend is atomic size. Atomic radius, kind of used interchangeably. Now, and you may go, who cares about atomic size? Or I certainly don't. Well, I do. Why? Because then I know why some people use nitrogen in their tires, or why my brothers, when they go to the sand dunes, they make sure they're in their sand rails that they're going to be putting nitrogen only in their tires. Well, it has to do with size. So, as we go down the periodic table, it does make sense the size is going to increase. So, let's say that you are going down group 1A, hydrogen, lithium, sodium, potassium, or rubidium, cesium, francium. Of course it's going to increase. It's going to get bigger. The reason is that you've just added another energy level. And so the big thing is it's going to increase as you go down the periodic table within the same family or group. However, what's really weird and did totally surprise scientists when they were studying the different atomic radii, as you go across the periodic table, like on the same period, but going across the periodic table, the size actually decreases as you go across the periodic table. So for example, if we were going across in period 3, starting at sodium, magnesium, aluminum, silicon, and so forth, all the way over there to argon, argon is going to be much smaller than sodium. Chlorine is going to be much smaller than sodium, but it's going to be a little bit bigger than argon, etc., etc. And again, this really did surprise scientists. So if it surprises you, well, then you're just like the scientists in the fact that it surprised them. So then they came up with reasons why, and one of them is the fact that since it didn't increase any more energy levels, I know, that was back in the last section, as you go across the periodic table, then As you increase the proton number, the positives, there's more attraction. Electrons are negative, so as you get a greater attraction, the size is going to become smaller. All right, so let's see. As we're going down the periodic table, notice our lithium, our sodium, potassium, it's almost double the size every period that you go down, every period number that you go down. The size almost doubles. Yes, it does get bigger. And yet here, as a whole, you will notice on our next slide that the atomic radius is going to decrease as we go across each period. So let's go back here to nitrogen now and say, well, why do some people, especially if they're racing and they don't want any air to be escaping their tires, why are they going to put nitrogen only in their tires rather than just using regular air? Well, that's because, yes, regular air is 78% nitrogen, but there are other things in it. There's other percentages. So rather than just having 78% nitrogen, they want 100% nitrogen. Why? Because it's a little bit bigger than other things that might be in the air there. That's one reason. So if it's a little bit bigger atom, then it's less chance of going out the itty bitty tiny microscopic holes. You know, in case you don't know this, there are little itty bitty tiny little holes in the material in your tires that very, very, very slowly over time that air will slowly leak out. However, nitrogen is just enough bigger that it really helps make it where the air is not going to be slowly losing air pressure. Which also means if your tires are going to be the right air pressure in them, then you're going to have better gas mileage. Another thing is if you got nitrogen only, this is not related to size, but if you got nitrogen only and there's no oxygen in there, then you're not going to have deterioration of your tires as quickly because there's no oxygen in there for oxidation of the rubber. But anyway, you may go, okay, atomic size doesn't affect me at all. Well, now you know why some people are going to put nitrogen in their tires. So let's look at the summary of trends in the periodic table. We talked about the valence electrons and we talked about atomic radius. Those are the only trends we need to worry about in this class. So let's see if we can do these. Put this on pause and answer these questions. All right, you're back. So, of the following elements, which is the largest, which is the smallest of these? Well, lithium, nitrogen, fluorine. Look and see where they are. Oh, they're all on the same period, period 2. So we know that as you go across the period, their size gets smaller. So the largest one would be lithium because it's furthest to the left, and the smallest one would be fluorine because it's, of those choices, it's going to be the furthest to the right. Okay, press pause and do this. Okay, now then. Lithium, potassium, and rubidium. You look and see where they're at. Oh, they're in the same family. They're in the same group. We know that as you go down the periodic table, within the same family, the size is doubles for each one. So the largest atom is going to be the one furthest down the periodic table, so our rubidium. And the smallest one is the one highest on the periodic table.